Well, say again?
We had a faculty meeting.
Oh yeah. I heard the ethics class and the.
Just one small piece of the whole.
What's going on? There's like 2 classes or something.
It's small bit.
There's always.
Well, no, that
something.
was just the end of the whole. There was a whole process
man.
of other things before that. Most of the information people.
I'm wired up.
Coming to the Warren Series seminar today. It's my pleasure to announce Ken Kamrin as today's seminar speaker. Ken got his bachelor's degree at UC Berkeley in engineering physics and a minor in math, and found his way to MIT as an applied math major for his PhD. Then he did 3 years as a postdoc at Harvard University, and then returned to MIT, where he's now a faculty member in the mechanical engineering department. Although he's very young of years, he's been awarded several honors, including fellowships from the Hertz Foundation, the U.S. Defense Department, and NSF. He received the 2010 award for the Nicholson Metropolis Award from the American Physical Society, and recently received the NSF Career Award for his work in computational physics and related stuff. So. And we'll see, I've seen him talk in other venues, and he's a very entertaining speaker with a flair for the dramatic. His stage name, you might say, is Kenny Kamrin. And many of his other performers know him for his role in Yoda, in the musical Star Wars. So maybe during the wine and cheese you can ask him about that. But I don't want to take up any more of his time, so I won't.
I love it.
Stop it. Say anymore and just say, Ken, the stage is all yours. Thanks for coming.
No, I mean, definitely. Thank you. I mean, if your mother runs a theater company and you get your PhD at MIT, you have to do the Star Wars musical. Like, it's just like this rule that you wouldn't be able to live with yourself if you avoided that opportunity. Great. So, yeah, thanks for coming, guys. So today I'm going to talk about modeling of granular flows. So first and foremost, the people who collaborated with me on this. So this guy here, David Hennon, he was my first postdoc, and he left my group last year to become professor over at Brown in mechanics. This fella here is George Koval. I've never met him before. So he seems like a great guy. We've had an online correspondence. He does some discrete particle stuff. I do some theory, and we've written a couple papers together. And these are my grad students, Sachit and James. And I mean, probably in this department, I don't have to convince you that it's important to kind of learn how granular materials flow and deform. In case you needed some convincing, they're really ubiquitous. They're really all over the place. Geological matter, pharmaceuticals, agriculture, you name it, okay? And of course, I love the hourglass because it's a great example of something that's so timeless and yet still so difficult to understand, okay? So why don't I just jump right into it with a really obnoxious question, all right? Which is, what's the constitutive law for granular flow? All right, so I say that because I know it's an obnoxious question, because it's an old question. You know, it goes back to Coulomb. You know, this is how he cut his teeth, was building fortresses for the French, and he made one of the first steps. And it's a difficult question, but it's made slightly more tractable because at the moment I'm just going to look at well-developed flows. So let's not look at small deformations. Let's imagine situations where I could be pouring grains. Say, you know, I want to look at that sort of situation. So let me just be a little extra clear about this. This isn't to suggest that there isn't a lot of stuff going on in the transient as you approach a steady response. All right? So we happen to know that for a fact. There's all sorts of work that's been done on this, critical state theory, what have you, that talks about the very complex interactions between the packing fraction of a granular assembly, the strength, and the evolution of internal variables as you shear. For example, just a simple shear over here This is work from Rothenberg showing how the strength and the packing fraction are evolving with strain. Okay? Very non-trivial. But what I'm trying to suggest is that we really don't even understand this part. Okay? Which is to say, once you're well developed, once you've undergone a lot of strain, what's your flow field? Okay? There's some very weird complications in answering that question. And so that is the part that I'm going to try to understand. Okay? So, without further ado, why don't I just jump into the problem, why it's difficult, how we're going to try to address this problem, and how it works. All right? So I would say probably in the last 15 years, there have been some good steps in progress on this question. And one of the most compelling steps is something that's called the inertial flow rheology. And what I like about this problem is that you can actually get pretty far in your understanding of the answer with simple dimensional arguments. All right, so I'm going to try to explain this, so follow along. All right, consider the following thought experiment. I give you two rough walls, fully rough, so imagine that you glue grains to them. Okay, and I give you a sample of granular material. And the granular material has certain properties. So each grain has a density. The density of that grain is rho s, rho solid. Okay? And there's a mean particle diameter. We call it d. There's also other grain properties that you would expect, like shape, friction, restitution coefficient, all those things. Those are all dimensionless properties. So let's fix the granular material. And let's stick a bunch of those grains in between those two flat walls until I get a nice dense packing. And then what I'm going to do is I'm going to apply a pressure to those two walls. So I'm squeezing those two walls together. And then I'm going to apply a kinematic boundary condition, where I actually move one wall with respect to the other. And I keep doing that until I approach a steady state. All right? So I approach some shear field going on inside, characterized by a shear rate gamma dot. So far, so good? OK, so what did I assign? I assigned the particle information. I assigned the pressure. I assigned the shear rate. So you can think of those things that I control. So I can, with those numbers, I can construct something that we call the inertial number I. So this is a dimensionless number that mixes and matches those numbers that I just told you about. The shear rate, particle size, density, and pressure. It's nice and dimensionless. So if you stare at that, you might say to yourself, it kind of looks like it's the shear rate, but it's scaled in a really weird way. Because it's got that pressure showing up as a square root in the denominator. All right? But that's what's called the inertial number. Now, there's a few different ways of understanding physically what this number means. Of course, the easiest explanation is I say, look, those were my inputs, and that's the dimensionless thing I can make with them. All right? Now, maybe a more interesting way of doing it, I don't know how much you guys like audience participation, but if we do audience participation, I can explain to you what this number means if you take your knuckles out and you try to drag them across each other. Okay? If you ever try to do this, you'll notice that it's not very smooth, right? So you can imagine your knuckles dragging across each other is like trying to shear a granular material, where you apply a motion, like gamma dot, but you see there's actually another time scale that occurs, because every time your knuckle rounds a crest, it slams into the hole next to it. Okay? And how much time does that take? Well, that's proportional to how hard you squeeze. Right? So you can think of it like there's actually two competing time scales here. One is the applied shear rate time scale, and the other one you can think of as the snapping time, how long it takes a particle to snap into the hole next to it once it rounds a crest. And that's what the other part of that number means. And that's how it becomes a dimensionless quantity, in case you're interested. In any case, you could say to yourself that dimensionless inputs can be put into the number I. What's the output that I care about? Well, what I care about is the shear resistance tau. So what was the stress needed to sustain that flow? If I wanted to make some sort of a rheological statement. Okay, so to make that a dimensionless output, I could say take that shear stress and divide it by the applied pressure, and that thing I call mu, just like I remember from the stress ratio mu, like a friction coefficient. And the basic principle was that mu, the output, should be a function of the input, or simply put, mu is a function of I. All right? So in a sense, from the dimensional standpoint, we believe that that's the rheology. Okay? It's very simple to construct this thing. And lo and behold, they do some tests. And here's what they find. They do simulations of experiments of this geometry, and it really looks like it kind of works. Okay? In simple shear, they do a bunch of experiments and simulations, and they find that mu looks like it is a function of I. This is like your flow rate variable, and that's like your loading variable. And it's characterized by a static friction coefficient. So we'd say that you don't flow at all unless mu exceeds this value. the shear stress over the pressure. But if you push harder, you will flow faster. Okay? So think of it like this. The general answer is that it looks like some kind of a Bingham rheology, but with pressure showing up in very weird ways. Okay? So after this was shown to be successful at modeling simple shear, people got excited and said, is this it? Is this the answer? Is this it, right? Because usually when I think from the standpoint of a rheologist or a fluid mechanician, what do? I would do a simple shear test. From it, I would extract a rheology. And once I have that rheology, I would say, oh, that's like how I get the viscosity. That's like my non-Newtonian viscosity. I'll just throw it into some Navier-Stokes solver, and now I can kind of solve everything, right? But then the parade kind of died down a little bit, because it turns out it only works in this geometry. Okay? Isn't that kind of unfun? It turns out there's more to the story than this, because granular materials are also extremely cooperative. And the cooperativity effects are something that you cannot capture with that model. Okay? That model would have you believe that if I told you the stress field, then that should imply the flow field, right? It's just like a regular old, funny looking, but just a regular rheology where stress gives me flow. However, I'm noticing that the particle size plays a bigger role. Okay? The particle size can influence the flow field too, in a very unique way. So on this slide here, I'm showing 4 different things. Very interesting manifestations of a cooperativity effect, none of which can be captured by the model I just showed you. So first and foremost, maybe the most obvious one, when you think about size effects, right? The particle size is playing a role in posing a length scale. Usually, if you're familiar with this literature, the first thing you'd look for was, do the shear features have the right size? Okay? When I'm shearing something, is the width of that shear correct? And the answer is, by and large, no, unless there's something missing in that model, because it turns out that the grain size, I'll talk more about this geometry, influences the size of shear bands much more than you would expect based on just that local rheology. So I'm going to use the terms inertial rheology and local rheology interchangeably. They both just mean this thing here. Okay? I call it local because it assumes homogeneous uniform flow. That's the only case where it really works. Okay? Okay, here's another weird effect. So according to the thing that I just showed you, you would believe that if I gave you a layer of grains on a rough surface and tilted it, that there would be one clean angle of repose, in the sense that if I tilt it above that angle, everything would flow down. All right? That's what you would believe if that law that I showed you was correct. And that's by and large kind of true, but something funny happens when the layer thickness becomes thin, which is that the thinner the layer gets, the steeper you need to tilt it to get it to flow. Okay? That's a sort of a strange effect, because it seems to be yet another manifestation of what I call the size effect or the cooperativity effect. Somehow, when you start competing on the size scale of the grains, something else comes in and makes it seem stronger by being thin. All right? And that's also the reason why it's so difficult to predict the outflow rate from an hourglass. You know, we have some empirical tools such as Beverlys correlation, but it's hard a priori to come up with the flow rate of an hourglass. But once you have it, it's relatively consistent. I mean, that's why we measure time with it. But trying to get it a priori is actually quite difficult. I'm also going to talk about this phenomena over here. This is known as the secondary rheology effect. I like to call it the motion-induced quicksand effect. Okay, so check this out. So suppose I give you a bucket full of granular material. And then what I do is I stick a weight on top, like a big ball bearing. Now, as long as I just let it sit on top there, it's just going to sit there. All right? But suppose I also install a turntable that lives on the very bottom of the bucket. All right? Right on the very bottom, really far from the top. The moment I turn that turntable on, it's going to turn the entire bucket full of sand into quicksand. And there is no more yield stress. So what you're seeing is an experiment where I set the ball on top, and the moment I turn on the turntable, far from that location, the ball is going to start to sink. So somehow, flow somewhere is causing fluidization everywhere. Very weird. And these are all sort of manifestations of this sense that there's a cooperativity going on and over distances that are somehow being distinguished by the size of a grain. So let's get into it. Let's sort of diagnose the problem directly by seeing how badly the local idea is going wrong. And once I see how the local idea is going wrong, it's going to give us some insights as to how to maybe fix it. So let's consider a silo flow. It's a nice non-uniform flow example. All right, we're all kind of used to seeing this geometry. The particular one I'm showing you here is a quasi-2D silo. So just imagine you've got two parallel glass plates and a flat bottom. There's a slit on the bottom as well. What you do is you fill this thing up with grains. And for your eye, we colored them initially in horizontal stripes, so you could see how it started. Then you pull out the plug and you let it flow, and sometime later it looks like this. Okay? Everybody got the geometry clear in their mind? So let's see how the local model does compared to what I will call the computer experiment, or which matches real experiments. So here's what we did. So I took that inertial rheology, and I did what I said before, which was I made it a constitutive relation in full by making it tensorial as sort of like a viscosity coefficient, and I solved it using the finite element method. And what you're seeing on top is the solution for the shear rate field that you get when you apply that. All right? So let me just sort of talk you through what you see, right? Here's the hole in the bottom, right? And what have you. So obviously you're shearing more at the bottom. You get these kind of arms of shearing that come out from there and take you all the way to the top. It's very beautiful patterns. You see you get shear band fingering. This happens sometimes in plane strain problems in plasticity. But I want to also point your eye to the following, which is that you see all these zones of black. Right? The black in this problem means no flow. And that happens because, like I said, that rheology has a yield criterion. So there are going to be zones that say my stress is too small, my flow rate is 0. All right? So this is very beautiful. But unfortunately, it's wrong. Okay? This is really what it looks like. Okay? Down here, this is a discrete element simulation where we simulated an actual silo flow with 500,000 frictional viscoelastic spheres. I'm going to tell you we also see the same thing in experiments, but it's nice to see this with DEM. By the way, I'll just give you a little bit of my own 2 cents on this. I like to use discrete element method simulations to calibrate rheologies to get my understanding correct. But once we've got it, we compare them to experiments. So that's what I'm going to do in this talk. So in the beginning, you'll see discrete particle simulations, and then the last half of the talk is going to be all comparisons to experiments. So what's funny about this is you'll notice that if you look around out here, this is a single snapshot, and we coarse-grained out all these fields. Really, everywhere is flowing. Right? There's no such thing as this zone where you go from flow to 0. Suddenly, the idea happens to you that by being adjacent to flow, you kind of have to flow too. All right? It's an interesting thought. And so clearly, you might say that one manifestation, like I talked to you about, is that the flow features aren't the right size. They're not spreading enough. Right? They're not spreading enough. So let's get right down to it then. I'm going to see if I can come up with a quantitative picture of the error with the local model that I can then use as my gauge to see if I fix the problem. So let's consider the following geometry. What's nice about this geometry, this is the annular shear flow. Okay, this geometry is as follows. You take 2 concentric cylinders. You fill it full of grains in between. You assign a rotation rate to the inner wall. You hold the outer wall at a constant pressure, but don't let it rotate. Okay, so you squeeze it in one way, and the other boundary condition is you fix it from rotating. All right, and what you do is you take this geometry, you let it flow for a long time until it gets to a nice steady state. And once you're done, what I want you to do is you go through the entire geometry and coarse grain out 2 things at all different locations. At every location, get the stress field, get the stress tensor there, and calculate mu from it. That's the shear stress over the pressure, locally. And everywhere, I want you to calculate I. That's that special number that looks like shear rate over square root of pressure. So what do we expect? Well, what I expect is if the local rheology is correct, then whenever I make the scatter plot of mu versus I, it would all land on one line. That would be the sign that the rheology is applicable everywhere. And if I don't land on one line, it gives me at least some sense of what's going wrong. Okay? So this geometry has a size, capital R, and I fixed the grains. Okay? The grains are fixed throughout all of this. They have a size D. So let's see what happens. Let's play the game. So you do this for a bunch of different choices of geometry size compared to D. All right? So I do a bunch of different steady flows where I make the geometry smaller or bigger, but I fix the material. When I'm done, I look at the steady flow field. I scatter plot mu versus I, and I see if they all land on one line. Well, that's what you get. So each of these data sets here, each of these colors, corresponds to a different choice of the geometry size relative to D. And if you didn't know any better, you would say, it looks like my selection of the geometry is changing the rheology, right? But you think about that and you go, that can't be right. I must be having a missing ingredient somewhere, right? This would seem to suggest, so these are the smaller geometries, and as you get, the geometry gets bigger and bigger and bigger and bigger and bigger, it approaches this line, the local law, which is what I thought it was always going to land on, right? If the local law were correct, that inertial law that I got from simple shear, all of those symbols should have landed on that dotted line, right? Instead, I see the mu versus I relationship is clearly not one-to-one. And furthermore, check this out. I'm flowing in a lot of areas where mu is less than what I thought was the yield criterion, right? Look at all this stuff that's where mu is less than mus down here, and yet I is not 0. And that's what we saw in that picture I showed you, right? I predicted there to be these big zones of no flow, but material was still flowing. Somehow, something is happening that's letting me flow, even though my stress isn't big enough. Okay? And just for fun, how about we try this one instead? So all of those were, each of those data sets was a different geometry size. Let's say I fix the geometry, and I run a bunch of tests where instead I just choose different wall speeds. And when I'm done, I'm going to scatter plot mu versus I and see where I go right and see where I go wrong. Okay, so where do I go right? Well, both of these seem to suggest that when the flow is very fast, that's large I, that one-to-one relationship kind of comes out. You see how they all kind of come together up here? But it's where I'm flowing slowly that things start to split off of my prediction from the local law. And it so happens that in this case, they split off in a kind of a new, also non-trivial way. Again, things seem to go wrong, and I start to see various different, what I would call a size effect. So something is going on, it has to do cooperativity, and it's screwing up these curves from all landing on the local rheology. All right? I guess, are there any questions at this point? So this is my diagnostic tool. All right? This is my way of figuring out kind of what's missing just based on steady flows. So I got interested in this, so my training is in constitutive theory, and I tried to think to myself, what could possibly be the missing ingredient that somehow rectifies all of that? All right? And I got very excited when I came across some literature in the emulsion flow community. All right, so you might say, what does a mayonnaise have to do with, gravel? But if you actually look at mayonnaise microscopically, it's a bunch of oil droplets, right? They have to slide past each other, kind of like ground, kind of like sand or granular material. And they also noticed that they had some funky size effects coming through. And I was very inspired both by the picture they painted, but more by the mathematical thing that they suggested you try. So here's the picture that they painted that explains non-locality. They do it through this mechanism here. They even named it the KEP mechanism. Now, I don't know if this is really true, but maybe it is. It's worth talking about. So what they suggest is that the reason you're getting non-local effects is because when there's a shear event, let's say one particle slides past its neighbor, what that can do is it can emit a little perturbation and stress. Think of it like it sort of causes a local fluctuation, which can travel some distance away. It has 0 mean, so I wouldn't change the local average stress tensor, but it's just some average time fluctuation that gets emitted. And that fluctuation can help to activate an event somewhere else nearby. So think of it like this. Flow can help me flow. Flow over there can help me flow over there. All right? So even if the guy's stress right here isn't big enough, if there's something nearby that's flowing, it can activate it so it can flow too. Okay? That was the picture that they suggested. And I was inspired by both the picture and by the final form. And I decided to propose the following that's inspired by this, but adjusted for granular materials. So here's what I think might be a better constitutive relationship for granular flow. Hear me out. I propose the following Landau-like form. Consider the following. Let's invent a phase field that I call G. Call it an order parameter, phase field, what have you. G stands for granular fluidity. What does G do? Well, the role that G plays in the end, it's a phase field, but it has a job. And its job is to help me correctly relate mu, which is the load intensity, that's the shear stress to the pressure, to gamma dot, which is how fast do I flow. That's the sole job that it plays in the mechanics. G relates how hard you push to how fast you flow. And I propose, and we've done a thermomechanical analysis of this equation to derive it, actually, in this paper here, if you're interested in rational thermomechanics. I propose that G evolves according to this system. Now, I wanted to point something out. So basically, what I'm suggesting is G is like an inverse viscosity in the sense that it relates how hard you push to how fast you flow. And I'm saying that that parameter is not a constant of the system or even just a function of stress, but rather you have to solve a PDE to get it. And that PDE depends on the grain size. Okay? You see that D is showed up in the relationship that determines this G field. Okay? And if you like Landau theory, this looks like an energy derivative, and this is the evolution, and that's the diffusion term. Now, this is what I might call the primitive form. I feel like this is the answer. This is where everything comes from. But for all intents and purposes, the part that got me most excited was not this full form, but rather what happens if you look at the form that the steady-state solutions of this equation satisfy. Now, getting steady state, so I want steady state, right? I want well-developed flow. So I want to know what happens for a long, in long time limits. When you do this, you find that there's a way to simplify this equation to figure out what are the stable steady-state solutions of this. And what you find is that the answer is what's below this blue line. All right. So here's what we get. I find that G, my fluidity, which is really my susceptibility to undergoing flow, is influenced by two things. There's one thing here which is a function only of the stress. This is shear stress over pressure, and that's pressure. I call that the local contribution. This says that my fluidity has to do with how hard I'm being pushed on right here. But I also get a contribution like this, which says that I can be more fluidized if neighboring material is disturbing me. Okay? And that's where del squared G is coming through. Okay? And if you look at the formula for G local that comes out straight from this, the formula for G local is this right here, which is in fact the inertial rheology. This is the standard inertial rheology. It's equal to the formula for gamma dot that I showed you on the second slide divided by mu, such that if you were to plug this in up there, you would just get the inertial rheology back. And that's what happens if there's no size effect or there's no gradients in the field. And that's the right answer, right? If there's no gradients, so I just have homogeneous flow, I should get the answer that I know works, okay, which is the inertial rheology. I should be able to recover that. And that's what happens here. Remember, inertial rheology has a yield criterion in it, so that I shouldn't be able to flow below a certain value. But the answer is that's not the total thing. There's also this term here, and it has its own length scale. And when you perform the math on this system, it comes out looking like this. Now, I have a number of different ways to show you that this is actually the right answer. It has one new, there's only one new thing in here. Do you see that I have a new material parameter? I call it A. And then I have the length scale D. So everything is scaled by the grain size. I have this sort of dynamic length scale that comes out. And there's one new material parameter that's going to show up in this whole process. And it's just whatever's in that numerator. We call it, it's dimensionless. We call it the non-local amplitude. So think of it this way. What I'm suggesting is the way that you would predict a flow, supposing that you knew the stress, for example, suppose you knew the stress field, here's how you would get the flow. I would use that stress field to construct this field, which is the local fluidity contribution, which is now really just a source. I then solve this PDE in full for G. I then take the answer and stick it up there to calculate the real flow. Okay? And note some other things about this. So because I have a diffusion coefficient here, I can never have sharp transitions between flowing zones and not flowing zones, right? That's good. And also, whenever G local vanishes, right, which was when I'm less than the criterion would suggest, so mu is less than mu s, this says that I can still flow. So I can still flow even if my stresses are too small. So there's a lot of reason to suggest that this might be a good idea. And if I put it back in full tensorial form, so this is in scalar form, if I tried to make a constitutive relation with this, it needs to be tensorial. So that's the model. There in the blue box. Let me sort of walk you through it. Clearly, there's still momentum balance, right? Divergence of sigma plus rho g equals rho v dot, F equals ma. But now, and I have the stress constitutive relationship, okay? Which is the statement that I showed previously, the definition of the fluidity, which relates now the stress tensor to the strain rate tensor, gamma dot. These are tensors. And G is showing up as the coefficient in there, okay? Because it's the fluidity. It sort of affects what I would think of as the viscosity. Okay? So G is its own thing that shows up in that formula. And G solves this non-local rheology. So every step, I'm simultaneously solving two equations, right? I'm simultaneously solving this one and this one together. So there's basically, regular momentum balance is 1 PDE. And I've added one more to the system. So I have to solve for one of the constitutive parameters by solving a PDE, then take the answer to update velocity to the momentum balance. There's a few ways of thinking about it, but that's really all it is. The local contribution here is still the formula that I would get if I assumed the local rheology was always correct. So this is the part that says if there's no size effect, everything will reduce down to this equation. And I get the same cooperativity length formula with that same unknown. So when you look at it, this is the model I'm proposing. How many unknowns are there in this model? Well, there's two material parameters that I call local. These are the ones that show up in this function, which I adopt from that local rheology. These are the ones that I get from simple shear. Now, these guys I already know. For most materials, it's been calibrated for a lot of materials now. So what's good about that is it sort of ties my hands. So once I tell you a material that I want to study with this model, I'm not allowed to screw with these ones because they're all tabulated. All right? Then there's the grain parameters. For example, the average grain diameter and the grain density. Those ones I'll leave open. You just tell me. Okay? Those ones also come in through this rheology. And there's really only one new kid on the street in order for me to run this model. And it's this thing A, which is whatever that coefficient is up here in that numerator. And so we've looked at a couple different simulations, and we've surmised what A is for a few different materials. For glass beads, physical beads, A is about 0.48. Okay, order 1 and dimensionless, so can't complain too much. And for discs, it's about 0.7. Also order 1, also dimensionless. And so remember, A is the non-local amplitude. It kind of measures how far away things talk to each other. A flow event over here will influence a flow event over there over a distance that is less than or equal to something given by A, right? Because that's like my cooperativity length. The bigger A is, the farther away two things can talk to each other. So it's not surprising, when you think about it, that A is bigger in 2D than in 3D. In 2D, there's many fewer ways to move around. So if I tweak something over here, it will influence something over there much further out than in 3D, if you can kind of see that. In 3D, I could tweak something here, and it won't influence as much of the neighboring material, but in 2D, it will influence a further sphere of influence. So let's see how well this thing works, now that I've taken you through this argument. With one new number here. So here's the deal. From here on out, I'm never going to change these numbers. Whenever I show you something that has to do with disks, I'm using A equals 0.7. Whenever I use spheres, I'm using A equals 0.48. And we're just going to see how well this works now. So that's the deal I'm going to strike with you. So let's return back to my litmus test. My litmus test was Koval's results, right, which showed that as I change the geometry or change the wall speed, it looks like I've changed the mu of I relationship. So I've reproduced that data from Koval. Those are the symbols. Okay, each of these colors represents a different geometry size. Each of these colors represents a different wall speed. If you remember, the local law, which is shown here with the dotted line, wasn't very accurate in the slow range. Right? Now, what you're seeing on top of that data set, the colored lines are the prediction of the non-local law. With only that one number and that one extra term added into the system, you can see that you've figured out every different way that you peel off of the local term. Right? And all we did was you added that one number. And somehow it manages to capture all these different ways that you divert from the local rheology in that system up here, which we studied. And as a result of having fixed the rheology, lucky us, we can now predict flows down to really crazy orders of magnitude. So this is the flow field in this field. So this is distance from the inner wall plotted on the horizontal axis. And this is relative velocity. That's velocity over the wall speed. And this is for 4 different values of the size of the geometry. These symbols are what you get from the discrete particle simulation, and the line is the prediction of this model, right? And so the predictions are now very good. Even, this is in log scale, all the way down into the tails of the flow. So you're getting the stuff that flows quick and the stuff that's just creeping along there over something like 3 or 4 orders of magnitude in speed. So this wouldn't be a constitutive law if it only worked in one geometry, right? You're not going to impress anybody if you can fit one geometry. You have to fit a lot of geometries. So we did the 2D example to death by thinking of all the simple geometries we can try with the same material, which would have all the same coefficients, and see how well this law works. So we did a chute flow where you have rough walls, gravity-driven. The particles are being driven down the chute by gravity. And we look at the flow field, which looks something like this. All right? And if you plot it based on the center of mass out like this, you can see how you do for different values of gravity. All right? So we did 3 different values of gravity. We did the computer experiment with particles, and we got these symbols. And then we took our same model, and we got those lines. And you can see 1, 2, 3, and a little bit further down, about 3.5 or 4 orders of magnitude, you capture everything. So you go all the way down into the tails of the distribution. You're still capturing the flow speed. I showed you this one already. How about this one? So like I said, I'm not changing any numbers. I'm just changing the boundaries. Okay? So we do simple shear, but in the presence of gravity. When there's gravity, it's no longer uniform. It makes the flow field look like this. It hugs the top wall. Okay? And again, it took the same model, and we computed a couple different flows with this by changing the value of gravity. And for each of those, we replicated those conditions and did our non-local model. And the symbols represent what came out of the computer experiment, and the lines are what we predicted. So you can see, again, we're doing very well on this, all the way down into the tails of the distribution. So we got inspired when we saw this because it looked like it not only, that dilemma of how mu of I splits up. We captured that. And then with the same model that captured that is now capturing other geometries. So we said, okay, let's see if the finish line is anywhere close by seeing if we can do a 3-dimensional problem. Okay? And from now on, so like I said, everything I showed you right now up to this point was discrete particle simulations. Why? Because I can see the flow fields very easily, and I can get stress fields from them. And I don't think you solve the problem unless you get both. But now that I think we got it, let's see if we can match real experiments. So from here on out, it's going to be physical beads. I'm going to use glass beads. And I told you the numbers we're using for that already. All right? And we're just going to see how well we can capture experimental data on glass beads. So what geometry should we try first? Well, we said let's try a really hard one. This is called the split bottom couette flow. Now, why did I choose this geometry? It's because it's hard. No existing continuum model was able to predict this. So we said, okay, I'm a junior faculty. I got to get a big result, right? So let's see if we can do the split bottom cell. Okay, what is the split bottom cell? Well, go to Target and buy a cake pan for like angel food cake or something, and get a jigsaw, and you cut a little circle out of the bottom so that it looks like 2 pieces, one piece that looks kind of like a top hat, and one piece that kind of looks like a lip. So it's really an annular trough, and you've made a slice down the bottom. Then I want you to fill it with granular media. And the way that you induce flow is you hold the top hat still while rotating the outer piece. Okay? And that creates a very non-trivial looking flow field when you do this. If you look down from the top, that's what it looks like. So imagine that the grains are colored initially half and half so that your eye can kind of see how they're swirling around. This is what it looks like from the top down when you rotate the bottom of a split bottom couette cell. And what people were excited about with this geometry was this flow field, which what's the flow field on the top? Right, that's what people were curious about. It looks kind of like a sigmoidal field where the stuff on the inside is sort of stuck on the top hat, and the stuff on the outside is rotating with the outer wall, and it sort of gets from one to the other over a very interesting shape. And the reason it's so interesting is for the following reason. So you might say, who cooked this thing up, right? Well, it does something weird, and that's why people like it. So as you fill this thing up higher and higher and higher with grains, that sigmoidal field that I call omega that you see on the top, what it does is, I'm plotting over here for different filling heights. For a shallow filling height, the width of that field is very skinny, and it stays basically close to the split. So here's the split radius. And then as you fill it up higher, the center moves inward, and the field gets wider. And you keep filling it up higher, it gets wider, it moves a little bit inward, until eventually you start to crash into the inner wall. These flows are, you filled it up so high that the shearing hit the inner wall. So these aren't so interesting. These ones are the ones that are more interesting. They have that sigmoidal shape. Now, why are those interesting? these curves here, it so happens, collapse onto one universal curve. Okay? If you just recenter them and scale the x direction by a linear factor, they all collapse onto one universal profile. Here it is. Okay, that's the universal profile that they all collapse onto. And that profile is an error function. I'm not saying it's approximately an error function. I'm saying it is an error function. It's closer than 0.5% away from an error function everywhere. And so people got very excited when they saw this because it seems to suggest that I have a geometry where on the very bottom, where the split is, the flow looks like a Heaviside function, right? Looks like a Heaviside function. And yet, as you get to the top, it turns into an error function. So the physicists went berserk because they said this is a solution of the diffusion equation, right? Heaviside goes to error function. That's, or you can think of if I give you a long bar and I start the left side at temperature 20 degrees and the right side at 70 degrees, and then I remove the non-conductive barrier and let it equilibrate, you'll see that it passes through the error function. So what's diffusing, they would ask. And so I thought to myself, well, we got this model. It's got this Laplacian term with the size effect. I wonder how we do. So in order to do this, we had to write our own finite element. Not many finite element methods that are built in will let you do something like we're suggesting, where you add your own new PDE to the system to evolve a state parameter which influences the constitutive law. So you had to do this yourself. So my postdoc at the time, Dave Hennon and I, we went ahead and we did this. We wrote our own finite element. So now we can implement our wacky model in any geometry, all right? So we wrote a 3D element and we implemented it in this geometry. And it does kind of what you would think, right? So this is a cutout in the ZR plane, as shown up there. On the bottom, you see the Heaviside function. Blue means I'm stuck on the inner guy. Red means I'm rotating with the outer guy. So you see the Heaviside function on the bottom, spreading out into an error function on top. And as you fill it up higher, the center of the error function moves in and gets wider. So we thought this might work. So we went ahead and we plotted our result compared to the experimental result on glass beads, and we got this. So we thought that's pretty darn good. Okay, this is the experimental result for different filling heights. But is it an error function? So here's what we did. We said, all right, let's get a bunch of shallow flows. So I'll do 22 different simulations where the filling height is very shallow and the grain size is small. 22 different simulations. Every one of them, I'll see if they collapse onto a universal curve, like I said before, and if they do, I'll check to see if it's an error function. So this black dust that you're seeing in the background, that's the flow fields of 22 different simulations, which all have managed to collapse together. And on top of them, this green line is an error function. So we're very happy to see that this model has managed to reproduce that very weird result. And like I said, maybe it's a gimmick, the whole error function thing. It got them into Nature back in the day. But I think this plot's probably even more important from a physical standpoint, which is what makes this problem hard. It's hard because you have a lot of lengths that have to all act in harmony. There is the length that corresponds to how high do you fill this geometry. There's a length corresponding to how big are the particles. And there's a length corresponding to what's the width of that band you see on the top. What's the width of that error function? We call it W. And the reason why this model is doing a good job, yes, it captures that shape, but more importantly, it makes all three of these lengths communicate correctly. Over here, you're seeing 165 experimental data points. Okay, my colleagues over at Leiden made 165 experiments out of this, where they varied the particle size, which here is indicated by color, and the filling height. And every time they would do it, they would do a flow, and they would measure how wide the shear band was on top. So we replicated every one of those using our theory, and we got those lines. All right? So the idea is maybe this is great, but the theory is correctly representing the way in which the filling height and the particle size work together to calculate the width of the shear band all the way on the top. So when we saw that this was working, we said, let's just kind of go out. Let's just find people who did experiments on glass beads. We have the numbers for those. We're going to try to copy those and see how well we do. So the next thing that people got excited about after the split bottom cell was presented in the literature was a little variant on the split bottom cell where they got rid of the inner wall. So it's basically you have a stationary platform and a lip that just rotates around it. And what this does is it enables you to explore deeper granular layers. So what happens is when the filling height is rather shallow, the flow field looks like the one that you saw before, right? We got a bunch of stuff that's stuck on the stationary inner thing, and the outer stuff is rotating. As you fill up higher and higher and higher and higher, a little bit of a transition takes place, where once it's filled up high enough, you find that there's basically a dome of static grains that are kind of stuck on the platform, and everything else is rotating around it. Do you guys kind of see this what happens here? So they thought to themselves, let's look at the transition of this problem by identifying the rotation speed of that particle right on the top center, which I call omega p. Right? So over here, omega p is about 0, and over here, omega p is 1. And how do you make that transition with something that people got interested in? So we said, fine, let's replicate that. Let's see how we do. So the experimentalists went and they did this, and they get the x's were their results for how the rotation speed of the particle changes as you feel higher. So we replicated that, and we got the red line. And we thought, not too shabby. So then we looked around, and we noticed that somebody else tried this with a different geometry, where they changed the location of the split radius, and they presented the blue x's, and then we changed our geometry and clicked enter, and we got the blue line. And so what's nice about this is it's suggesting that even as you change subtle things about the geometry, this non-local model is able to sniff out what you did and change the answer. So we said, okay, look, let's just see if we can throw any flow of glass beads at me, and we'll see if we can predict it. So we looked in the literature, and we found some data on a standard angular flow compacted by gravity. So you basically just a more standard set, three-dimensional. Gravity keeps it down. You rotate the inner wall, and you get a flow field like this, which I've replicated over here with the velocity versus distance from the inner wall. And they use glass beads, and the data that they obtain is shown here. And I don't know if you can tell, but in the background there's a line, and that was our prediction. Then there was another data set we found for these three-dimensional plate dragging problem, where you take a bed of sand and you put a rough plate on top, and then you drag it, and it produces a flow field as shown here. And the circles are the data points for the flow field that they found. So this is velocity versus depth. All right? And they only presented one data set, only one set of circles. So we're like, oh, man, let's see if this works. So we clicked enter, and we got that solid line. So this is all using the same PDE system with all the same coefficients, as long as they said they use glass beads. So we just used them. Now, some of you might say, okay, if this works, are you overkilling it with the form of the equations you used, right? Remember that thing that I showed you previously, the dynamic length scale? I told you it does a funny thing, and all it needs is one coefficient on the top, what we call the A parameter, right? Did you overdo it, Kenny? Do you really need something crazy like that? Well, let's see. So what I'm suggesting is a form that looks like this, where alpha is 1/2. That's what came out from my primitive system when I simplified it. But did I really need to do that? So what if I supposed alpha was 0? That's the engineering approximation of just make it constant. Okay? And some of the folks in physics thought that alpha would be 1. So we said, okay, let's not be dogmatic. Let's just see what happens when I change these and see how well I do. So it turns out that when you try to fit this data that I showed you from these various experimental apparatus with different values of alpha, the only choice of alpha that fits all of them is 1/2. The other ones will get you qualitatively there, some to a more degree than the other, but the only one that gets every one of them happens to be the one that came from the theory, which is 1/2. So remember I told you there was a table of different phenomena that in the very beginning that all relates back to cooperativity. So one of them I said was correcting the flow features, and that was what I just tried to show you, but there was other stuff too. Remember that quicksand phenomena that I told you about, where you can move something over there, and now it makes it easier for you to flow over there? So here's a little movie that I think captures that very nicely. Now in this movie, there's an experiment. This rod has a constant force on it for the entire movie. At some point, they're going to rotate the inner wall. And when they do, suddenly that rod can now move. All right? Previously, the rod was stuck. By rotating something far away, the rod can now glide all the way through. And as long as that wall keeps spinning, the rod is going to keep on gliding through. Right? Now, note that all the way, if you look at the flow field out here, it's basically 4 or 5 orders of magnitude smaller than it is here. So it's not, the grains aren't really moving. Yet somehow, this faraway motion is fluidizing where the rod is. Now, eventually this wall is going to stop, and the force on the rod will not change. But when it does, suddenly the rod must stop too. Okay? So a constant force pushing on a rod will do two things. If the wall is stationary, there's a yield value. And if you don't push hard enough, you don't move. However, if the inner wall is moving, then it will move for any force, right? Whatever force you apply will make the rod move as long as the wall is moving far away. And in fact, it has a very funny form. This is what they found in the experiments when they did this. They found that if you doubled the wall speed, it kept the force fixed, you double the creep speed of the rod. So you spin the wall 2 times faster, the rod will glide 2 times faster. Okay? And if you increase the force, it has a very weird dependence. It's like a cinch or exponential dependence on the force. So as you push harder, the rate at which you glide through increases exponentially. So we thought, okay, let's give it a shot. Let's see how we do with that. So we decided to try a simpler version of this geometry because of computation time issues. So we said, let's do a 2D version where I have basically a rigid disk, and I'm going to apply forces to it. And I'm going to see how it does. We implement the model. So first things first, when the inner wall is stationary, we find indeed that there's a yield force that's necessary to get the thing to flow. So if you don't move the inner wall, you have to push above a certain value to get the thing to flow. But let's suppose then you start to rotate the inner wall and you look at what happens. Now when the inner wall is rotating, what we find is that if you move the wall 2 times faster, it moves 2 times faster. We find this linear relationship. If you double the wall speed, you'll double the creep speed. In other words, the only time scale in the problem is the time scale of the moving wall. So if you make that faster, the rod will creep faster. Furthermore, we find that if you apply a force to this thing and you start to increase the force and ask how much faster does it creep, you get, this is in semi-log. Okay? This is a semi-log plot. We actually get that cinch. It's approximately a cinch. I mean, I don't know exactly what it is. So it looks like our non-local model has actually almost very closely replicated this function. Okay? What about that other phenomenon I told you about? I told you about the fact that thinner things act stronger, right? So let's see how we do. First and foremost, I want to remind you how this works. I give you an inclined plane flow problem with a rough bottom, and I try to flow grains down the inclined plane surface. Normally speaking, I think that there's a repose angle, such that if once I hit that angle, everything will flow. But in reality, what we find is that thinner layers require more tilt to flow. So in fact, if you made a phase diagram, where one axis was how thick is the layer, and the other axis is what's the angle of incline, it actually looks something like this. This is experimental data from Pouliken back in 1999. And what you're seeing is the thinner layers here have to be tilted up to a much higher angle in order for it to start flowing. And the line that divides the flowing and not flowing regions is called the Hstop curve. Okay? They call it this, it's really a stopping curve, because the way they actually conduct this is they incline it to the point of flow, and then they slowly decline it until the flow stops. And then they put a data point down. That's how they do it. So they call it the stopping curve. All right, let's see how we do. Now, this problem boils down to a question of when is the no-flow solution the one that the system's going to find? Right? Remember that I showed you this dynamical system. Sometimes it has multiple solutions, and the stability will change. And so the question boils down to, when is the static solution the one that the system's going to find? Static solution means no fluidity. G is equal to 0. So we return back to the primitive form, because I have to do a dynamics on this. And I have to solve this and figure out what is the bifurcation line between the stable solution being the flowing one and the stable solution being the not flowing one in this geometry. Now, in order to do this carefully, I have to do a really good job making sure I use the right boundary conditions. Now, for everything that I've shown you previously, we've used the conduction-free boundary condition, dg/dn is equal to 0, just because it's the easiest and least disruptive one. However, this is a thin geometry. We're going to get to very thin layer heights. And if you don't get the boundary conditions correct, you can basically make the answer whatever you want. Okay? So I don't want to play that game. So what we did was we looked into the data. There is some data on what shear flows look like in this geometry. And from those, we infer that the shear rate tends to go to 0 at the rough wall, and it tends to flatten out near the top. So from that, we surmise homogeneous boundary conditions that are good for this geometry would be g equals 0 on the bottom, dg/dn equals 0 on the top. That's what we basically calibrate the boundary conditions. And note that they're still homogeneous. So they will not tell you whether or not it flows. Right? They don't answer the question for you. So it could flow or not flow based on that. So we went ahead and we stabilized and we saw what happened. So the data that I showed you previously, Pouliken's bifurcation line for glass beads, those are these circles. And the theory predicts that solid line. Okay? So it looks like the theory has predicted the Hstop curve. And I want to point out a couple things. One, this is the same material parameters that were used to predict the flow of beads in the split bottom cell. Right? The only thing they told me was they used beads, and that this is a very different problem. I'm not calculating a flow field. I'm telling you whether or not you will flow at all. Okay? It's a very different question. So size-dependent strengthening and calculating size dependence of a flow profile are very different. But needless to say, if you do incline it high enough so that it can flow, the model does predict the correct field again. Okay? And again, if you didn't have the non-local term, you would have always gotten the dotted line, which would have missed all of this data down here. Okay? So let me take a moment now as I'm finishing up the talk. So I tried to just tell you that we've done 3 different manifestations of non-locality, right? Size dependence in the flow field, right? The shear features need to be the right size. The motion-induced quicksand effect, flowing over there makes my rheology change over here. And the smaller is stronger size effect. So I told you that I think that this is a really cool question, right? Can you predict how fast an hourglass flows? So what do we know about this problem? You're laughing. Okay. If anyone would know, you would. So anyway, here's what we kind of know about this problem. There's something called Beverlys correlation from the 1960s that seems to do a fairly good job. It's an empirical rule, but it's a pretty good job at predicting how fast an hourglass will flow. Basically, it looks like follows. So Q is your mass outflow rate, and D is the size of the orifice. As long as the thing is filled up enough and wide enough, it looks like it obeys a law like follows. And this is in 2 dimensions. It looks like it's the orifice size minus some multiple of the particle size to the 3 halves. Okay? And this is the square root of, this is gravity. This is 9.81. And you have 2 empirical coefficients, C and K. So you look at this and you say, oh, come on, Kenny, you can do it, right? There's a size effect, right? Wouldn't that be cool if this model could predict Beverlys coefficients for you? So you don't have to go and do a couple experiments in your proposed silo to get C and K. You could just say, hey, I got grains. BUS equals this, B equals that, A equals that. Run your simulation and tell me the Beverlys coefficient so I can make my silo, right? Because it really does seem to work. This is experimental data showing that 3 halves collapse. Now, unfortunately, I don't have an answer on this yet because this is a much harder problem to simulate than all the other ones I just showed you. Okay? Much harder problem to simulate, especially with a non-local term. But this guy here, Satya Dinatunga, he's a smart kid. He's my grad student. He's going to get there because he has to if he wants to graduate. But in the meantime, we've already come up with basically the framework that's going to let us do this. Okay? So if you subtract out the non-local part and just look at the local formula, but add this. This is what I call the disconnection rule. Now, most plasticity theories consider just a dense granular material, but don't account for the fact that you can also throw grains into the air, and then they separate, and they don't support any stress. And oftentimes in problems with granular materials, you'll have a zone that's flowing like a dense material, then it's going to open up and then reconsolidate, right? That's a very difficult problem for an elastoplastic framework. But we have a framework that does this now. It's a continuum framework based on a meshless method called NPM. So here's what it looks like, for example. Here's an NPM simulation of a silo drainage. And I want to remind you, this is a continuum simulation. Okay? Every one of those points that you're seeing is a material point. All right? It's just a node in our scheme. And you're seeing plastic strain rate being plotted. And this is the inertial rheology plus disconnection. Now, the disconnected zone you were seeing here was the grains as they fall. And yet, when they land, the scheme is designed to know that they've landed, turn it back into an elastoplastic solid, and let it flow again like an elastoplastic solid. And when you do this, you can see that we actually get that 3 halves power. Except we don't have this term yet, because I don't have a size effect in there yet, which is why he needs to do that if he wants to graduate. But we got the 3 halves, right? But while I'm on the subject of this, what I call the trans-phase model, right? It lets you go between static, dense flow, and gas, right? We've been playing with this a lot recently, and it's actually quite a lot of fun. Like, let's suppose you just want to take a handful of sand and throw it at the wall. Okay? So blue here represents disconnected gas-like material, and light blue represents dense, which means either static or plastically flowing. And what's interesting is you can just take a handful of this stuff, throw it at the wall, and you can see that it's doing what you'd expect. It's forming a heap. It even looks like it's splashing around. But remember, these aren't real particles. These are just implementing a continuum model. And recently, we've tried to expand this to the impact, right? Granular impact is very difficult to do because you always go through every phase, right? You throw something down, and you're going to make parts that look solid, liquid, and gas within a tenth of a second, okay? And so what's nice about this is you can study this problem. So these are elastic objects impacting a bed of grains. And you can tell when you look at the square that they're elastic, right? The square kind of jiggles around after it makes main contact, and the sand kind of fills the space there. What I liked about this is when you actually look at the solution over the course of less than a tenth of a second, you can still see that you're solving plasticity because you're seeing the remnants of slipline theory come through, okay? I don't know. I was trained on slipline theory from this guy's book. And as this indenture comes through, you can actually see you're forming the log spirals that you get from Sokolovsky theory. So it's like as it's entering the material, it's pushing it out of the way like you would expect from those analytical solutions, which is kind of pretty. And what's nice about this method is it's very general, it's meshless, so you can go through all sorts of crazy topological changes, right? I can actually throw something, have it completely embed itself into the sand, then have the sand come over and fold over it, okay? And this is an elastoplastic solver with an opening rule. So I don't know if you're familiar with finite element methods or what have you, but it would be almost impossible to do this with a finite element method, when in reality, it actually has a finite element step every moment. If you're interested in how this method works or don't already know it, I have a backup slide. But it even kind of does what you expect based on the experiments. If you look at the path that it makes as it goes down, and you even get a little plume in the middle as the grains come back on top, which is what's seen in the experiments. So with that, oh, there's one more thing I want to show you before I close. So the end of the talk gets more fun and less mathematical. So as we started to play with the transphase model, which gave us the ability to simulate things that are very difficult because they mix things up too much. So it's really tough to solve plasticity, but with this method, we can do it. We got interested in trying to see if some of the empirical approximations that people have been using in the field called pterodynamics, which is locomoting on sand, actually came from plasticity, or whether they are some freakish thing in the experiments. So one of the things I got very excited about, which is an empirical reduced order theory that my friend Dan Goldman suggested. It's called resistive force theory. So resistive force theory does not try to answer the question of what is a granular flow field. It tries to answer the question, if I give you an arbitrary object and submerge it in sand and drag it in a direction, what's the resistive force from the sand? It just tries to come up with a drag rule for you. And it generates it based on the shape of the object in a very weird and simple way. Resistive force theory would have you believe, now I was very skeptical when I saw this, that the way to figure out the resistance on an object moving through sand is all you got to do is you take the object that you're interested in. Say this circle, okay? And I imagine that the circle is composed of a bunch of little plates, all right? So just break it up into a bunch of little plates. Then go back to the drawing board, take each little plate individually, and do an experiment. And move it like it would have moved if it was part of the circle. Okay? Do that with every single little infinitesimal plate. When you're done, add up all the forces. And that should be the answer. Okay? Now, I just showed you a really wacky looking model, right? And you're trying to tell me that that's all you need to do to get a good approximation if all you want is drag force. So we took our transphase model and made it even simpler by getting rid of the rate sensitivity. So it's just Drucker-Prager plasticity plus an opening rule. And so we did the plate problem in our finite element simulation. We moved plates at a bunch of different angles and in a bunch of different directions. And then we did the full problem. So we tried a diamond-shaped and a circular-shaped object and saw how we did. Okay, so in each of these demonstrations here, the solution from the full plasticity problem, where I took the real shape and dragged it, and I look at the tractions and I look at the net drag force, are the blue arrows. And the red ones are what I get from this very simplistic resistive force theory. And the total force, which is shown in the center, is actually really darn good. Okay? So if all you want is drag force, it seems like this might be all you really need to do to get a good approximation, which is nice because then it gives you the ability, without having to solve any PDEs, to do things like this, which is to predict how an arbitrary wheel will roll through granular material. So these blue vectors here are the predicted resistive forces from the theory. And I have an experimental lab that I'm starting finally because we have some experiments we want to do. And this is the mock-up wheel of the same situation. All right? And we rotated it. It's the same shape, has the same weight, and the same rotation speed. And you can see that it actually predicts the final translational velocity very well, and even the power consumption, right? The torque times omega gives you a rate at which you consume power to roll the wheel through. And I thought that was very interesting, that we can actually use this now, and we can do model-driven design, where let's suppose I want to figure out the best wheel. I literally want to reinvent the wheel. I want to find the best wheel tread to drive over a sandy terrain. Well, I can either make 10,000 experiments until I find one that works, or I have a very simple model now that seems to work pretty darn good. I can actually optimize over the model instead, and I can do that on my cluster, hopefully pretty quickly. Right? So there's a thought that we might be able to invent the best wheel, and I actually believe why this works now, because it actually comes from plasticity. Needless to say, I don't know, do you guys know what this is? This is the Mars rover, Spirit, 2008. Yeah, this is a time-lapse movie of it stuck in the sand for a month, right? So we're really bad at dealing with locomotion in granular media, especially when things like sticks in the mud, like changing the value of gravity, come out. But what's great about knowing how resistive force theory comes from plasticity is I can easily change the gravity. Once you give me the sample and I understand why it works, we have a hope of maybe saying, dear NASA, here's what you did wrong, right? I will tell you how to make it a scaled experiment that will correctly mimic the Mars rover, because they tested this thing in like the Mojave Desert and it was doing great. It's amazing what happens when you change gravity by a factor of 2/3. Anyway, I think I'm a little over time, so I'll stop here. Concluding remarks. Let's see. The majority of this talk, I was telling you about how you need to have a non-local effect. If you don't have a non-local effect, you will not get the cooperativity, which in the systems that we typically look at in many cases is very dominant. Okay? You can't just ignore it. All right? And the manifestations of non-locality that people have studied, including grain size dependent shear features, smaller is stronger, and what I call the quicksand effect, where motion somewhere turns everything into quicksand. It turns out that all of them are manifestations of one model. And I tried to present that model, and it only requires you to introduce one new material parameter. And at the end of the talk, I guess I kind of just ventured into Funville. We have a numerical scheme that is actually enabling us to solve plasticity equations as material travels through many different phases of matter. And it's revealing new insights into things like drag laws on granular media. So, with that, I'll thank the funding sources here and ask for your questions.
Okay, thanks for a great talk. That was really inspiring. It's very fun.
Thank you.
So we're, as Ken mentioned, a little bit over time, but maybe we can have time for a couple short questions, and then, as you all know, there's wine and cheese reception afterwards that we can ask more questions. So, Andrew?
I'm trying to ask a question. It's fascinating what you have said, but I have two questions. One, you use the word steady, but some experiments are not steady.
Right.
It's the one you showed. It's a transient.
Which experiment?
Well, the rotation, the quit.
None of the ones I showed you had ill-defined steady states.
No, not this one. Yeah, it's the upper right.
This is steady.
What do you mean it's steady?
This
You
is steady.
show-
So if you keep rotating
No,
this, you'll reach a steady
it's
state
not
velocity
steady.
field.
I'm sorry. This is the beginning and grows.
But I'm not modeling the transient part. I'm only modeling the part when it gets to steady flow. So you let this thing flow for a while until you have a non-changing velocity field.
That was my question.
Yes,
The
sorry, yes.
picture is not steady.
Yeah, sorry, yeah.
transient.
If I showed you the steady, it would just be a big mess of color. Yeah, so no, this is still in the transients.
Okay.
But you rotate this thing a couple times, you get a steady flow.
Great.
Okay.
Second question, rate. Because it's like Bingham, you said in the beginning.
The local laws like Bingham.
Yeah. But do you have something like viscosity?
So this is a great question. Okay, I want to point something
Because
out.
Then
Yeah.
it should be function of viscosity. Meaning
So
fast flow, because
faster, you should have to push harder to flow faster, right? Like viscosity.
yeah, but this very rotation I can do very, very slowly. There's no really rheology.
So that's a great question. So let's look at something that I didn't say, but I should have, because maybe I should have predicted this. Let's look at what happens as I change wall speed in my litmus test case. Right? Remember, this was my litmus case, what I used to try to match the rheology. So remember, I let this is my geometry, and I do a bunch of tests where I change the inner wall speed. Every time I do that, when it gets to steady state, I cross-plot mu versus I. So I want to draw your attention to these 3 plots right here. Okay? Those 3 plots correspond to the 3 slowest velocities that were tried. And I want you to pay attention to one thing, which is, this is the locus of mu versus I for each of these 3 different slow wall speeds. Observe that the range of mu is the same for all 3. But the range of I, which is my flow rate, is different for all 3. So what you're suggesting is there shouldn't be a viscous effect. Eventually, if I'm flowing slowly, it should be basically rate independent. But that's what this is showing, right? I'm seeing that the same stress field appears to correspond to different flow rate fields, right? These are off by an order of magnitude apiece. And yet the model which I presented to you is capturing that. Okay? Why? Why is it capturing that? Good question. When I'm in a zone, when I'm flowing slowly, I get zones where mu is much less than mus. What it does is it makes this term vanish. What's left is a PDE that is linear in the flow speed, right? It's linear in g, so I can always scale it up or down. So this magical equation is able to sniff out when I lose my rate dependence and is able to replicate that effect. It's very subtle. Very subtle. I don't expect that explanation to be sufficient. Okay? But the moral of the story is you're right. You do lose your rate sensitivity when you get slow, and it's evident in the data. But the non-local model is able to capture that because of the fact that it works even where the local contribution is dead. The local contribution is the one that looks like viscosity. Okay? It's a great question. I mean, this was part of the reason why I knew it couldn't just be any non-local plasticity model. It had to have that rate independence kick in somehow in zones where mu was less than mus. That's why it's really not arbitrary that it's this form. There's very few models that can actually capture all of these things and put them together into one form.
Very, very interesting. This is good that you have the slide up. I'm intrigued how you got from the nonlinear equation. Because even if g dot is 0, it's still g squared. And
like, how do you get from this to this?
Yes.
Yeah. So
what exactly is that g log? I mean, is that part of the solution or?
Yeah. So let me give you a brief explanation for how you get. If I say this is the actual form and this is the one that you can use if you just want steady state.
Yes.
So how do you do that? It's a great question. So let me sort of guide you through the mathematics that you take. So the first thing that you do is you create what's called a local or homogeneous solution. So imagine that you solve for a function which assumes chalkboard with no chalk. Okay, let's assume that G is the sum of 2 pieces, okay?
Yeah.
And that G homogeneous solves this equation. So let's assume G homogeneous is what the solution would be if there was a size effect. Okay? So it's equal to basically 0 minus that term in the brackets. And everywhere you see a G, replace it with G homogeneous. Okay? That becomes what I call G local. Okay? Then what I do is I make the assumption that the actual solution is equal to the homogeneous one plus some correction. And I expand in the correction and I get that.
So you were lucky because it's nonlinear.
No, I did it reversely.
Yeah.
I told you it was not chronological. This was the thing that I liked. Okay? But I realized that wasn't the original starting point. It came from something.
Yeah.
And it was only then that I realized that that's actually an approximation to the full Landau form. I'm just being honest.
And it works.
That's how they always work, right? You see the steady thing and you realize, how can I get that answer?
And the nonlinearity never comes into the state. You can always cover all of the cases because the nonlinear equation is non-unique. You know?
That's right.
And
But the stable solutions are, right? So when you solve this, you only take the stable answer. That's the magic. That's how it picks out which is the right answer to go with.
Very nice. Very nice.
Thank you. Yeah.
Can I give it to you and you can pass it down.
That's a good question. That's a really good question.
That's very nice.
Yeah.
That is good.
My question is biased by my own background. You have a non-local solution, but a non-local in a very non-classical way.
That's right.
Typically, you have stresses dependent on some other fields, like strains or strain rates in the neighborhood. That's what the non-locality is. But in your case, it depends on completely different variable.
That's right. Sorry, I lost my screen. Oh, okay. Yeah, I can explain it. Yeah.
And I didn't see how that variable is related to something physical, because it is the phase field that is artificially introduced there.
Okay. This is a great question. So just to restate the question a little bit. When you look at classical gradient theories, usually you'll see something like the flow resistance is a function of the total strain and the gradient of the total strain. That's your typical Afontis theory or Flood-Hutchinson closure, right? This is saying something different. This is saying I invent a field which is not determined just about what happens locally. I have to solve a PDE, which relates that field to everywhere else through its boundary condition in order to figure out the flow here, okay? So you might say to yourself, what in God's name is this thing, right? What is this field? I swear, I should have paid you guys to just answer. Yeah, these are all very, very difficult questions that I've been thinking about now for about a year. But let me show you where we are with that one, okay? That means I have to go through all this. So you might ask yourself the question, what is this fluidity field? Okay? So I decided that I wanted a student to answer this in the same sort of ultimatum. Yeah, you want to graduate? Well, you have to answer this one. Okay, so what is the physical origin of the fluidity field? Here's what I think it is, okay? And this is not a done question yet. There's a question mark on that. I don't know the answer. Maybe you can help me. Let's look at a great example of a geometry in which I know the stress field very well, okay? But the flow does not match the stress field according to the local law. And that's this one here. I call this the plate tracking geometry, which is simple shear, but with gravity present. Because when you look at this, it's actually simple to know in advance what is the shear stress and pressure everywhere. The shear stress is merely constant everywhere, and the pressure increases as you go down because of weight. When you look at the ratio of shear stress and pressure, that tells you then that there's going to be a zone where mu exceeds what I called mu s, and a zone where mu is less than mu s, and some line in between them that separates them. Now, if the local law that I talked about was correct, everything below that line should be static. And of course, it's not, which makes it a great geometry to figure out where am I getting that little extra juice that's helping me flow where I shouldn't be able to flow. So we did some discrete particle simulations of this geometry. And what I'm plotting up here at different heights is what mu versus time looks like when you actually conduct the flow. Okay? Now what's interesting is you see it's fluctuating a lot, right? But the average is right where I predicted it to be. So let's look below the divider line. Everything down here was supposed to be static, but check it out. You see these fluctuations? They're big. Typically, they're big enough to bring me above my threshold. So the fluidity is somehow measuring how many extra fluctuations I get in my mu because I was adjacent to material that was honestly flowing above mu(s). Okay? That's the hypothesis. Does that make sense? So it's some measure of fluctuation in mu, which adds on to the mean. And just because my mean value is below mu(s), doesn't mean my value won't always be below mu(s). Weird. That's where we are right now with it. Yeah.
So I find it a fascinating lecture and interesting model. What puzzles me the most is that the rheology is all scalar rheology.
Uh-huh.
And so I'm very surprised that what that means, I guess, is that in a complex stress field, that the different stress components are correlated because they all come from the same single scalar G.
That's right.
I'm just wondering what you would
So-
say about that.
Let me tell you what I would say about that. I thought I added this extra slide. Here it is. Okay. So you're saying, look, why are you getting away with this scalar thing, right? I have a stress tensor, a flow rate tensor, and a G field. Well, maybe there's anisotropy, maybe there's fabric, maybe there's something that makes it more complicated. So that's a great question. So let's look in and see what happens. So here's a silo flow, all right? And what we did was we took a snapshot of the well-developed flowing state, a single snapshot in space. And you can even see the grains in the background. And we decided that what we would do is we would coarse grain over boxes of size 5 particle diameters, just 5. Okay? And we looked into each of those boxes, and we coarse grained out using the Christopherson formula. What is the stress tensor in that box? You get it from the particle contacts. And what is the velocity gradient tensor? Then what we did is we converted the velocity gradient into the strain rate, so it's symmetric. And we looked to see, does the stress and strain rate co-align? Well, you can see for yourself. Okay? This is in the middle of a flow process. And to within about 3 degrees, the stress and strain rate fields are coaxial. Now, what does that mean? That means that if I need to make a model, all I need to do is do the scalar part, and then when it comes time to write it down, I have to go through all the movies again. Do, 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 do. Splashy, splashy, splash. Da, 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 do, 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 do. Check it out. Sigma, scalar, strain rate. So under your nose, I snuck in the coteractionality hypothesis, but I knew it was good, so I didn't feel like I needed to tell you. Now, sometimes when I show this slide, I'll show a picture of what I just showed you, in case people like you who realize that this has to be more complicated would ask, what about the directionality between dp and sigma? Well, it turns out codirectionality is a very good hypothesis, even in the presence of all this non-local stuff. Yeah.
Well, I'm sure there are many more questions, but since we're over, maybe we should adjourn to the wine and cheese.
Great. Thanks, guys. Yeah.